Hi there, this is Truth Socrates. Welcome to today's video where we will talk about the alternating series test. So far we have seen the divergence test, the integral test, the ordinary comparison test, and the limit comparison test. Now, the integral, OCT, and LCT tests work only on positive series. In other words, the terms have to be positive. They could also be zero. We don't make an exception for zero. But in today's video, we're going to learn about alternating series in general and how to apply this test to decide if an alternating series converges. So unlike our previous tests, this test is going to work only on a specific kind of series, namely an alternating series. Before we see what it does, though, let me remind you that you have already seen an example of an alternating series when we talked about geometric series. When the common ratio is negative, then when you square it, you get a positive number. When you cube it, you get a negative number. So the series alternates between positive, negative, and so on. All right, so let us see how to generalize this. Here you go. This is what an alternating series looks like in general. We will start with a sequence b sub n, where n goes from k to infinity, of positive terms. Again, if you want to allow zero, that's not such a big deal. We will form the infinite series, which look like summation n equals k to infinity, negative 1 to the n, b sub n, or negative 1 to the n plus 1, b sub n. Everything is the same in these two notations, except the exponent of negative 1 in the first series is n, but in the second it is n plus 1. Right? So the only difference, of course, is the plus 1, and negative 1 to the plus 1 is negative 1. So in other words, this second series is simply the negative of the first series. And of course, taking the negative does not change whether a series converges or diverges. So for practical purposes, these two series are essentially the same. They're just the negatives of each other. All right, so as we mentioned in the beginning, a geometric series where the r is negative is an example of an alternating series because if we had like negative 2/3 to the n, we can take out the negative 1 and we'll have a separate factor of negative 1 to the n times 2/3 to the power n, right? So in the notation that we introduced in the definition, the b sub n is the 2/3 to the power n. As usual, we will let the original sequence, which makes up the series, be the a sub n, right? So let me warn you that we heard the symbols a sub n and b sub n when we talked about the OCT and the LCT, but in the AST, alternating series test, the b sub n means something different. It essentially means the absolute value of the a sub n because we're taking away the factor of negative 1 to the n. Okay, so let's take a look. Let's go back to the harmonic series, which is made of the harmonic sequence, 1 over n. We know from the integral test that the harmonic series diverges. The integral of 1 over x dx is ln of x. From 1 to infinity, ln of infinity is infinity. So it diverges. However, let's take a look at negative 1 to the power n plus 1, 1 over n. Okay, so because we're starting at n equals 1, don't divide by 0, 1 plus 1 is 2, negative 1 squared is positive 1. So this alternating series starts with positive 1 over 1, and then negative 1 over 2, positive 1 over 3, negative 1 over 4, and so on. So let us take a look at what is going on with the partial sums. All right, so here we go. The first partial sum is just the first term, which, as we said, is 1. And then the next partial sum is 2. We add a 2, but that means that we subtract 1/2. So we get 1 minus 1/2, positive 1/2. Okay? So if this were just the plain harmonic series, we will have 1 plus 1/2, or 3 halves. No, this time we only get 1/2. Big difference. Next partial sum, S3. So we will add to our previous partial sum the next term, which is A3, which is positive 1/3. So we're adding 1/3 to 1/2, we get 5/6. Next partial sum, to S3 or 5/6, we will add A4, but A4 is negative 1/4. So we are subtracting 1/4 from 5/6. Okay, so we get 20 minus 6, 14/24, which reduces to 7/12. Okay, so instead of showing you the diagram that I have down here, let's go to GeoGebra and reconstruct it ourselves, and maybe we'll use different colors. All right, here we are in GeoGebra. So I hope you remember the sequence command, and we demonstrate it here by plotting the points which correspond to the terms of our alternating harmonic series. So n will go from 1 to 10, and we are going to plot points. X coordinate is n, y coordinate is -1 to the n plus 1 over n. Now, in order to appreciate our sequence better, I adjusted the scale on the y-axis so that 1 is very big, right? So are you ready? Let's show what this looks like. Boom, there you go. So the first term is just 1. The next term is -1/2. The next term is positive 1/3, -1/4, positive 1/5, -1/6, and so on. Okay, we actually have room. We can go all the way to 15 if you like, even 16. All right, there we go. Okay, so next we're going to plot the partial sums. Okay, so to do that, let's duplicate this sequence, this command. Okay, there we go. There are now 2 of them. So instead of just the term, what we're going to do is we're going to use the sum command in order to get the partial sums, right? So just so we don't wreck this, I'm going to delete that. Sometimes GeoGebra does strange things if you push the wrong button. So let me pause it now. All right. So I'm going to put sum of -1 to the k plus 1, over k, comma, k will go from 1 to n. Ooh, okay. Thank you, GeoGebra. You did not freak out for a change. So here are the partial sums that we saw in the PDF. Okay, so the first partial sum is covering the one from the sequence. So let me hide this a minute. All right, there you go. So it's still there. And if I hide the other one, that's the partial sum. And then we got 1 minus 1/2, which is positive 1/2. And then to that, we added the 1/3. So we get this. And then we subtract the 1/4, add the 1/5, and so on. Okay. So I hope you appreciate that kind of like these terms are all positive and these terms are all negative. They're like 2 kinds of partial sums. Okay, so if we have for n equals 1, 3, 5, 7, 9, 11, 13, 15. So those are odd subscripts. And here we have for 2, 4, 6, 8, 10, 12, 14. Those are even subscripts. So I hope you kind of guess that we are forming a decreasing sequence here, and we are forming an increasing sequence here. Okay, so just like the limit of the terms is obviously 0, these partial sums appear to approach maybe, hopefully, the same number, the same partial sum. Okay, so yeah, maybe it's like approximately y equals, what shall we guess? 0. Let's try 68. Oh, okay. That looks like a possible limit. Or how about 0.69? Ooh, maybe that's even better. Okay, so it looks like the sequence of odd partial sums and even partial sums are like approaching the same horizontal asymptote. And we will find out, of course, that that is indeed the case. Whenever I see this diagram, it kind of reminds me when you're getting on the freeway, okay, and the vehicles on your left are also trying to get off the freeway on the next off ramp, so you're kind of competing for the same lane. That's just me. Okay, so let's go back to our PDF because we are going to formalize this concept of what is called a subsequence. All right, so suppose we have a sequence of natural numbers, I sub m. M goes from 0 to infinity, where I sub 0 is the initial value of the index, the starting term basically of our sequence. And then we will pick another natural number, I sub 1, another one, I sub 2, another one, I sub 3, and so on. Now, this new sequence, I sub n, will generate what is called a subsequence by using these as the index, the value of the index n. In other words, we will look at a sub I0, a sub I1, a sub I2, and so on. Okay, so instead of defining the sequence I sub m separately, we will generalize or rather notate this sequence as simply a sub I sub m. So notice I said sub twice. A sub I sub m. A has one subscript, I sub m. I has a subscript, m. Right? So you might think of it as a double subscript, or probably more appropriately, a nested subscript. You have a subscript within the subscript. Ooh, profound. So m will go from 0 to infinity, and as usual, m does not have to start from 0. It can start at 1 or 2, and so on. All right, so that is relevant to us because we observed something about the odd partial sums, and it's different from the even partial sums. Okay, so from the sequence of partial sums, S1, S2, S3, and so on, we are going to create two subsequences of partial sums. We will have the odd partial sums, S1, S3, S5, and the even partial sums, S2, S4, S6, and so on. How do you make an odd number? Well, you have a choice. You can be like 2m plus 1 or 2m minus 1. But if you start m at 0, then to create 1 from 0, you're going to need 2m plus 1. Okay? For the even partial sums, I started at m equals 1, and then that's going to get me 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on. Okay? Could I have started m at 1 here? Sure. In this case, then, to produce 1 from 1, you will need 2 times m minus 1. Okay? So, yeah, but it doesn't really matter because we're going to do something to the odd partial sums and something different for the even partial sums, as we are about to see. All right, so we're going to create those two subsequences of partial sums when we prove the alternating series test, which goes like this. Suppose you have a sequence b sub n from k to infinity of positive terms, and these terms are monotonic decreasing, they're getting smaller and smaller, and they converge to 0. Okay, so you have to check two properties, monotonic decreasing and converging to 0. Then, the two alternating series that we defined earlier, they both converge. And again, that only makes sense because if this converges, then its negative, which is this series, must converge, and vice versa. Okay, now, if one of these conditions does not hold, the part where your terms converge to zero, then we already know from the divergence test that the alternating series will not converge. It will diverge or perhaps diverge to infinity or minus infinity. Oh, wait a minute. Can that happen? No, you're getting positive something, negative something, positive something, negative something, and they're not approaching zero. No, you cannot diverge to infinity or to negative infinity. You will simply diverge. Okay, so it's a very bad situation. Okay, so what we're gonna do is we will pretend that we start at 1 instead of k in general. The idea, of course, when you have general k is practically the same, right? And let's consider the second form, negative 1 to, n from 1 to infinity, negative 1 to the n plus 1 b sub n, which means we have b1 minus b2 plus b3 minus b4, and so on. Okay, so it alternates positive, negative, positive, negative. All right, so we saw the example of the alternating harmonic series earlier, and let us generalize what's happening to our partial sums. Okay, yeah, let me go back just a little bit. Okay, there we go. So our first term is b sub 1. That's our first partial sum. Now, we are going to write the odd partial sums on the left and the even partial sums to the right, because we're going to do some magic with these two groups. Okay, so to b1, we subtract b2, so s2 is b1 minus b2. Okay, next partial sum s3, we will add to s2 the next term, which is b3. So b1 minus b2 plus b3. All right, I hope you get the pattern. Next, we will subtract b4, so we get this. And then we will add b5, we're going to get this. Then we'll subtract b6, we're going to get this. Okay, so if you're taking notes, feel free to put the next s below s5. Okay, so after 6, we're going to get s7. Okay, test your understanding. What will you see here for s7? What will you see here for s8? What should it look like? Okay, so if you want, you can pause the video and move on later. I am going to move on now. Okay, so our strategy will be to use the monotone convergence theorem. We notice that one of these partial sums is increasing, one of them is decreasing. So we're going to hope that that's true in general. It is. And we're going to see that both of these subsequences are bounded. So by the monotone convergence theorem, both of them will converge. Now the tricky part, not so tricky, is we're going to show that they converge to the same limit. So in other words, these cars are getting on to exactly the same lane on the freeway. And of course, the guy in front of you is trying to cut you off. Okay, so how are we going to do that? So let's move on to this screen, and then let me adjust myself over here. So the key property for this part of the proof is the decreasing property of b sub n. Okay, as we said, it's getting smaller and smaller. b1 is bigger than b2, b2 is bigger than b3, b3 is bigger than b4, and so on. Okay, so we are going to rewrite the previous table using properties of arithmetic and parentheses. Okay, so remember that, let's start with S3. S3 is B1 minus B2 plus B3. Okay, so if we factor out the negative from the B2 and include B3, then that plus should become a minus. Okay, that's the mistake that you make all the time, right? Forgetting to turn a sign because you factored out a negative. Now, luckily, we won't have to do that for the even partial sums because we're going to group the B3 and the B4 together, the B5 and the B6 together. Okay? So in the same way in S5, we will also factor out the negative from the B4. And if we include B5, we're going to have to turn that plus into minus. Okay? So back over here, we have B1 minus quantity B2 minus B3, and then minus quantity B4 minus B5. As I said, we don't have to worry about the even part because we're simply grouping the plus with a minus. We're not factoring out a negative. Okay? So now, because B1 is bigger than B2, B1 minus B2 is positive. Okay? But similarly, B2 minus B3 is going to be positive. B3 minus B4 is going to be positive. B5 minus B6 is going to be positive. Okay? So, what does it mean? From B1, we are subtracting a positive number. And then from S3, we're subtracting another positive number. Which means that the odd partial sums are decreasing. How about the even partial sums? B1 minus B2 is positive. We're adding another positive number. We are adding to that another positive number, and so on. Okay, so therefore the even partial sums form an increasing sequence, and we're going to have to address boundedness. So because the first sequence is decreasing, then the biggest value B1 will be an upper bound. And since the even partial sums are increasing, and that's positive, 0 is a lower bound. Okay, so now we have satisfied the monotonicity requirement for the monotone convergence theorem. We just need the boundedness property. Okay, we have an upper bound for the odd partial sums. We need a lower bound. We don't have a lower bound just yet. We have a lower bound 0 for the even partial sums. We don't have an upper bound just yet. Okay, what we're going to do though is we're going to cleverly regroup the terms in our sequence, kind of in the opposite way. Okay, so this is how we are going to regroup exactly the same terms that we saw earlier. So in the original table, we had B1 minus B2 plus B3 minus B4 plus B5 here in the bottom. Notice we are just reversing the parentheses. Okay, you can see S5 over here and the same S5 down here. Okay, but instead we are grouping B1 minus B2 together, and then that is originally plus B3, B3 minus B4 together, and then B5. Okay, and now for the even partial sums, we're going to do the opposite. Okay, so we will start with B1 minus B2, and then we should have plus B3 minus B4. We're going to leave the minus B4 alone. Let me scoot this up a little bit so you can see. We're going to leave the minus B4 alone, but we're going to factor out the negative this time from B2, and we're going to get negative quantity B2 minus B3. All right, that's plus B3 over here. That's minus B3 over here. All right, so continue with the pattern. You'll get for S6, B1 minus B2 minus B3, and then we will subtract B4 quantity minus B5, and then we will have the minus B6 by itself. Okay? Now, why does that help? Well, it's because, what did we say? Our odd partial sums are decreasing, but everything here is positive. Positive, that's positive, positive, everything here is positive. Okay, so therefore 0 is a lower bound for the odd partial sums. That's what this sentence says. But on the other hand, for the even partial sums, excusez-moi, sorry about that, I summoned Adobe on the internet. Here we go. So what we're saying about the even partial sums. From B1, we are subtracting B2, and then from B1, we're subtracting this positive number, B2 minus B3, and then we're subtracting another positive number. Keep going. From B1, we're subtracting this positive number, subtracting another positive number, subtracting yet another positive number. Okay, so therefore, all of these numbers are bigger than B1. From B1, we're taking away something, 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 something. All of these partial sums are smaller than B1. Okay, so in other words, both of these partial sums are bounded below by 0 and bounded above by B1. Ta-da! We have paid for the monotone convergence theorem. So both of these subsequences of partial sums are convergent, and we can write their limit. We can say that the limit of the odd partial sums exists, and the limit of the even partial sums also exists, but there's one small catch. They may not be the same. So we will call the limit for the odd partial sums L1 and the limit for the odd partial sums L2. Okay, we must show that L1 and L2 are exactly the same limit. How are we going to do that? Well, what is the difference, literally, between the odd partial sum S2n plus 1 and the even partial sum S2n? You are missing term number 2n plus 1. So that is a sub 2n plus 1 as the difference. Okay. However, a sub 2n plus 1 is simply going to come from the sequence b, in this case from b sub 2n plus 1, and we have the alternating factor negative 1 to the 2n plus 1. Remember, it's negative 1 to the n, b sub n. But we know that b sub n goes to 0, so therefore a sub 2n plus 1 also goes to 0. And there you go. That is what we need, because we can now take the limit. Since we know that a sub 2m plus 1 is s sub 2m plus 1 minus s sub 2m, its limit is the same as this limit, but we can break up this limit into two separate limits, and we get L1 minus L2. Aha! So L1 minus L2 must be 0, the limit of a sub 2m plus 1. L1 must be equal to L2. All right, so therefore, both sequence of partial sums converge to exact same limit. L1 and L2 are exactly the same. All right. All right, let's go back to our workroom and look at a couple of examples. Now, let me warn you that the notation that we're using for the AST is quite different from the way that we used A sub n and B sub n in the OCT and the LCT. Not so much A sub n. A sub n is the original alternating sequence in the AST. It's also the original sequence in both the OCT and the LCT. Okay? But in the AST, the B sub n means the absolute value of A sub n. You ignore the negative 1 to the n. Okay? So this is not the same way that we use B sub n in these two tests. All right? Let me just warn you. They don't mean the same symbol. The symbol does not have the same meaning. Okay, and to recap with the alternating series test, you have to show that this B sub n has limit 0 and they form a decreasing sequence. Okay, so sometimes it's obvious that the B sub n is decreasing, sometimes it's not so obvious. Sometimes it's obvious the limit is 0, sometimes not so obvious. Okay, so let's go back to the alternating harmonic series, and we saw from the picture, the graph in GeoGebra, that it looks like it's approaching a limit that the series converges. Okay, so of course the B sub n in this case is simply 1 over n. Ignore the minus 1 to the n plus 1. The positive portion is 1 over n. Okay, is the limit 0? Yeah, we've seen that a million times. So whose limit is obviously 0. Is it decreasing? Yeah, as n increases, 1 over n decreases. And also, obviously, decreasing. Okay, so by the AST, the alternating harmonic series converges. And as a matter of fact, while we are here, does it matter if that is n, or how about n to the 2/3? All you do is change 1 over n to 1 over n to the 2/3. Does that still go to 0? Yes. Is that still obviously decreasing? Yes. Okay, so that alternating series will also converge. And if you change that to 5/3, yeah, that doesn't really make much of a difference in this case now, does it? That's because this is alternating. And so it's a different series. It's not 1 over n to the 5/3. It is negative 1 to the n plus 1 over n to the 5/3. Okay? Before, we could use the integral test. Now, nope. The integral test does not apply to the series. But, of course, we have the alternating series test that we can apply to this series. All right, now let's go back to another infinite series that we've seen before when we talked about the ordinary comparison test. We have the infinite series summation n from 2 to infinity of ln of n over n to the 5 over 7. ln of n is bigger than 1, so ln of n over n to the 5 over 7 is bigger than 1 over n to the 5 over 7. And we know from the integral test that this series made of 1 over n to the 5 over 7 is divergent. It's a p-series. P is 5/7, which is less than the magic number of 1. Okay, so now, what if we turn this into an alternating series? Right, so again, it's now a different series. We'll start at 2 minus 1 squared positive. So we will start with positive ln of 2 over 2 to the 5 over 7 minus ln of 3 over 3 to 5 over 7 plus ln of 4 over 4 to the 5 over 7 and so on. Okay, so we want to know if we can decide whether this alternating series converges or diverges. We have to look at b sub n. We ignore the minus 1 to the n. So our b sub n is exactly what we saw before, ln of n over n to the 5/7. Okay, so we must show that the limit at infinity of b sub n is 0, and b sub n is forms a decreasing sequence. Let me move myself up over here. Scoot, scoot. Okay, so what we're going to do is, since that can be treated as a function, okay, we can find the, oops, I keep using the wrong scroll bar. Since that is a sequence that comes from a function, we can use calculus to apply the first derivative test to see if our function is decreasing. And we can use L'Hopital's rule to see if the limit is 0. Okay, why don't we do that first? L'Hopital's rule is fun. Can we apply it? ln as we go to infinity, infinity, infinity to the 5 over 7, also infinity. So that is the limit as x approaches infinity of the derivative. The derivative of ln of x is 1 over x. So delete 1 over x. Power rule, the derivative of x to the 5 over 7 is 5 over 7, drop the power, subtract 1, 5 over 7 minus 1, 5 minus 7, negative 2 over 7. This feels familiar, doesn't it? Yeah, because we just did it in the last video or so. Okay, so now we need some creative flipping. What do we have? Yeah, sure, we can flip the 5 over 7 into 7 over 5. Let me clean this up entirely. So we have 7 over 5 from the 5 over 7. 1 over x. X should go down to the denominator. And you know what? I'm going to keep the x to the minus 2 over 7 in the denominator, even though it has a negative exponent. And that's because we are going to combine these two, so we might as well put them side by side. X to the 1 times x to the minus 2 over 7. So we're back to 5 over 7. 7 minus 2 is 5. So this is equal to the limit as x approaches infinity of 5 times x to the 5 over 7. Okay. And of course, as x goes to infinity, that goes to infinity. 1 over infinity times 7/5. Who cares? That limit is 0. Okay, and of course, we use L'Hopital's rule in the first step. The rest was algebra and taking limits as usual. Okay, so now we need to show that our sequence is decreasing so that we can apply the first derivative test to the parent function, ln of x over x to the 5 over 7, positive 5 over 7. Okay, so we have the quotient rule. Okay, so remember, low d high, less high d low, and so on. Low, and then d high. The derivative of ln of x is 1 over x, low d high, minus high, so ln of x, keep it, just copy it, d low times the derivative of x to the 5 over 7. Oh, wait a minute, we did that down here. So we can just copy that, square the bottom, x to the 5/7 squared, you multiply 5 over 7 by 2. Okay, not 25 over 49, okay? Please double the 5 over 7. Okay, so we have some simplifying to do. And what are we gonna get? Oh, check it out. X to the 5 over 7 times 1 over x. So we're subtracting 1 from 5 over 7. We're going to get minus 2 over 7. Aha! So we're going to get the same factor, x to the minus 2 over 7. And we simplify this product. Okay, that is great because now we can factor out the x to the minus 2 over 7 from both terms. Let me put it on the next line over here. And we can put it in the denominator. Okay, so we're going to take this out, and it leaves behind a 1, not a 0. Okay, stop that. In the denominator, we will multiply times x to the positive 2 over 7. Okay, so now we have this accounted for as well. Okay, so yeah, review, x to the minus 2 over 7. There are 2 of them. Factor this out. You are left with a 1 from that term. This simply goes away. X to the minus 2 over 7 goes to the denominator as positive 2 over 7. Okay, and then for the coup de grace, we shall combine those two. 10 plus 2 is 12, x to the positive 12 over 7. Okay, so first derivative test. A function is decreasing if its derivative is negative. Is this derivative negative? Well, we have a denominator x to the 12 over 7 that's positive. So the sign will depend on the numerator. Okay, so this numerator must be negative. For the derivative to be negative, we must have this numerator to be negative, less than 0. Okay, so in other words, what do we want? So we can move this to the other side, and then we'll get ln of x times 5/7 greater than 1. So let's rewrite this inequality as ln of x times 5/7 to be greater than 1. Okay, so it's not clear to me that that is true or false. But, well, let's move the 5/7. In other words, some more, we must have ln of x must be greater than 7/5. Oh, wait a minute, that's 1.4. Okay, so that worries me a little bit because ln of x goes like this. Ln of 1 is 0, ln of e is 1, and e is bigger than 2. Okay, so this is definitely not true in general, which is only true when x is bigger than, solve for x, e to the power 7/5. Okay, so careful. We want x to be bigger than e to the 7/5 because we want ln of x to be bigger than 7/5. How much is that? It's about 4.055. Aha! So this is not true in general. Okay, so let's go back to our original series, which is this. So ln of n over n to the 5/7 will be decreasing only when n is at least 5 or greater than 4. Okay, so beginning at n equals 5, the derivative will be negative, and that is where it will be decreasing. Okay, however, that is only a slight technicality. We said in the integral test that the condition that your function, your parent function that we're integrating, is decreasing can be replaced by the phrase eventually decreasing. So this is true also for the alternating series test, and this sequence will eventually be decreasing. You don't even have to wait very long. As soon as n is bigger than 4, the terms of your sequence will be decreasing. You want to check? Let's go to GeoGebra. All right, here we are. So we have ln of n over n to the 5/7. I have hidden the stuff we were doing earlier. So let's see what it looks like. There you go. So between 1 and 4, you're still increasing. But after you cross 4, you are now decreasing. And this should worry you a little bit. Oh, maybe there's a horizontal asymptote. But we do know that this sequence will converge to 0. So you want to look some more? Let's go up to 65. Ooh, we got more dots there. And yep, they're going lower. Okay, so they're still above 0.2, but shall we go to 165? I hope I don't break GeoGebra. Yeah, we got some more dots. Yeah, so now we are below 0.2. Yes, still getting lower and lower and lower. We know, because we know calculus, we know L'Hopital's rule, that the limit of the sequence is going to be 0. All right, so the alternating series test remains true if we insert the word eventually. Oops. There you go, eventually before decreasing. And so our alternating series converges by the AST. Okay, so for our last bit, we're going to go back to our PDF and we're going to learn a little bit about the error approximation that we get by approximating an alternating series with a partial sum. We did that for the integral test. Let's see how to do it for the AST. All right, so in the integral test, we have a formula for E sub n. We said that it's between integral from n plus 1 to infinity and integral from n to infinity. Okay, so we're going to do the same thing for alternating series, but first we need some notation. Okay, so let's take a look at this alternating series. I can go all the way there, and you can still see it. Okay, so let's start with b1 minus b2 plus b3 minus b4 and so on. We will approximate this alternating series with S10. Okay, so we will add up to plus b9 minus b sub 10. Okay, now what did we say? Well, if S is the exact sum of the series and we subtract S10, we subtracted these terms, then the first remaining term, surviving term, will be B11, okay? And it's going to be a plus B11 followed by minus B12 and so on. So this is the error that you get by accepting S10 as an approximation for S. That's the difference between S10 and S, okay? But now we know that B11 is bigger than B12, B12 is bigger than B13, and so on. So B11 minus B12 is positive, B12 minus B13 is positive, and so on. So let's do the trick that we saw earlier. We can pair these in two different ways. We have B11 minus B12, one pair, plus B13 minus B14, another pair, plus B15 minus B16, another pair. Positive, 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 everything is positive, so therefore E10 is positive, okay? So in other words, the error that we get from approximating S10 from S is an underestimate, okay? And that's because S10 plus E10 is S. E10 is positive, so S10 is smaller than the exact value for S. It is an underestimate. Okay, but now we can regroup by leaving B11 alone, factoring out the minus from B12, joining it with B13, but that means that that plus turns into a minus quantity B12 minus B13. Repeat, factor out the minus from B14. You also have to put minus in front of B15, and so on. Okay, so from B11, we are subtracting a positive number, another positive number, another positive number, and so on. So therefore, our error is smaller than the first term, B11. Okay, so put them all together. It means that E10 is between 0 and B11, the next term in the sequence, which has a positive in front of it. Okay, now what if we did S11 instead? Okay, so we do the same thing, but add one more term, B11, and if we subtract all of this from S, the first surviving term will now be B12, but it's subtracted, so there's a minus in front of the B12. Plus B13 minus B14, and so on. Okay, so this time E11 will be negative, okay, because we can factor out negative from B12 minus B13, and then negative B14 minus B15. Everything will be negative. And we are starting with negative B12, adding something positive, adding something positive, adding something positive. So E11 is bigger than negative B12. Okay, so this time E11 is negative, which means that S11 is too big. S minus S11 is a negative number, so E11 must be negative. S11 is an overestimate. Okay, it's bigger than the actual correct sum. Okay, or another way to say this is that the negative of E11 is positive and smaller than B12. Okay, so therefore we can summarize this by saying that the absolute value of the error E sub n is smaller than Bn plus 1. Okay, so let's see how this works with our alternating harmonic series, and there is a statement of the general principle. Okay, let's take a look at the alternating harmonic series, and let's go all the way to, how about there? Okay, we have the alternating harmonic series. We can use GeoGebra to get S10. Well, yeah, we already plotted them. So S10 is about 0.6456. Okay. So according to our theorem, the error for the partial sum S10, the error E10 is bigger than 0, of course, in absolute value. We already know the error is positive, smaller than B sub 11, which is 1 over 11. Okay, that's approximately 0.0909 and so on. That's kind of big, isn't it? Okay. So the exact sum, remember that this is an underestimate. The exact sum could be as big as this estimate plus this error, which is 0.7365. Ooh, yuck. Okay, we do have a computer though, thank you GeoGebra. And so we can compute S100, right? And GeoGebra will tell us it's about 0.68817, right? That's, again, an underestimate, but this time the error is smaller than the next term, which is 1 over 101. It is now 0.009, okay? So that's a much better result, of course. The correct answer could be as big as this number plus this number, okay? But since that number is not very big, yeah, it's still in error, but at least the error is a lot smaller than 0.09091. Okay, I'm going to tell you a secret. We know exactly what the sum of this alternating harmonic series is. I'm going to show you. Okay, so the alternating series is, of course, just minus 1 to the n plus 1 over n, alternating harmonic series. So we know that this converges by the AST, and we want, I'm going to show you exactly what is the exact value of this infinite series. Okay, so as not to spoil the surprise, I will try S100, and we said, GeoGebra said something like 0.688. Yeah, I think this is just about what GeoGebra came up with as well. Okay, let's try 1,000. What do you say, Maple? We get 0.69264. Okay, so that's quite a bit different from 0.688. Okay, so what is the exact value of this series? Is there a famous number that you know close to 0.69? Well, maybe 0.7. Maybe the exact value is 0.7. Nope, it is not 0.7. Okay, I'm gonna reveal the value by doing something indirectly. That's E. Okay, so what I'm going to do is I'm going to plug this thing into e to the x. Okay, like, what are you doing? We get 1.9999999. Okay, so if I told you that if we plug in the correct sum, the exact sum, into E, we will get a nice number over here. Yeah, that's not so much a nice number, but this will turn out to be a very nice number. A very nice number close to 1.999. Well, there's definitely one nice number very close to this. In fact, it's so close, it's close by 0.001. That number is, of course, 2. So if e to the exact sum is exactly 2, and we will show this later in part 3, when we talk about power series and Taylor series. And so, if you want S, that S is the exact sum of the alternating harmonic series, we should get, ta-da, ln of 2. That will be the exact sum of this alternating harmonic series. You don't believe me? Maple, how much is ln of 2? It's about 0.693, which is pretty close to that number. All right, so that is our video for today. I hope you enjoy it, and I will see you soon when we talk about 2 different kinds of convergences: absolute convergence and conditional convergence. So until then, I hope you enjoy the rest of your day. Bye.